In this video, we're going to look at the binomial expansion of the binomial a plus b. We're going to raise that binomial to the nth power, and we'll begin with n equaling 0. So the quantity a plus b, all raised to 0, well, for the most part, almost everything raised to 0 is always equal to 1. The only thing that you cannot raise to 0 is 0. That's called an indeterminate form, but we're not going to worry about that. So just remember, anything that's raised to 0 is almost always 1. We'll now move on to making n equal 1, and so we just have the quantity a plus b raised to the first power. Any quantity that's raised to the first degree, first power, is always going to be itself, so it's going to be the binomial a plus b. But as we increase our value of n to 2, our work for the quantity a plus b raised to the second power is going to be more involved because we need to remember to FOIL. And so if I go a times a for the first terms, that's a squared. If I do the outside terms of a times b, that will be ab. If I do the inside terms of b times a, that's just another ab. And then the last terms, b times b, will give us b squared. If you combine the middle terms, you'll get the perfect square trinomial of a squared plus 2ab plus b squared. Since we're now being asked to expand a plus b's quantity raised to the third power, we have to take the trinomial result we did for a plus b quantity raised to the second and multiply that by yet another binomial a plus b. So when we take two terms and distribute it over three terms, we will generate 6 terms. Those 6 terms are in the green ribbon on the bottom. Let's go through the work for each of those terms. We take the a squared from the trinomial, multiply it by the a of the binomial, and we'll come up with a cubed. Take the 2ab from the trinomial, multiply it by the a of the binomial, you get 2a squared b. B squared from the trinomial times a of the binomial gives you ab squared. We're done with the a's in the binomial, so we'll move on to the b's, in which we take a squared times b, giving you, well, a squared times b. 2ab will be multiplied by b. That will produce 2ab squared. And finally, b squared times b will give us b cubed. There's your 6 terms. But of those 6 terms, there are some terms that are like terms and can be combined. We can take the 2a squared b, add it to another 1a squared b, and we'll generate the second term of our expanded result, 3a squared b. Just like we can take ab squared, add it to 2ab squared, and come up with the third term, 3ab squared. So in the end, the expansion of a plus b quantity cubed equals a cubed plus 3a squared b plus 3ab squared plus b cubed. So now if you're going to expand the quantity of a plus b all raised to the 4th power, you're going to have to take the answer from before, a cubed plus 3a squared b plus 3ab squared plus b cubed, and you're going to have to multiply by another a plus b. That's a 4-term polynomial being multiplied by a 2-term polynomial, and when you distribute, you'll get 8 terms. And many of the terms can be simplified into the middle terms, and so the quantity a plus b all raised to the 4th is a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. So if you are being asked to expand the quantity of a plus b all being raised to the 5th power, you could continue the recursive process of distributing to the previous term and multiplying it out, or if you are going to be asked to do yet another one, maybe to the 6th power, you could determine if there's a pattern that's actually being involved, and you could use that to expand more efficiently. So I've decided to rewrite all those terms and by chance put it in this particular shape. Does this shape by chance seem familiar to you? Would a pattern be more recognizable if I would show you all the coefficients in bold, including those of value of 1? How about now as I put the focus solely on the coefficients? If you look carefully, you might recognize Pascal's triangle, and that's in fact what you will want to use as you apply those values and coefficients to what is known as the binomial theorem. The binomial theorem is written as a sigma notation type problem. It's sigma notation, again, basically means it's a sum of a series of terms. In this case, whatever your value of n, and n being a non-negative integer, is going to produce n plus 1 terms. So our row 6 is going to generate 7 terms. The terms will be generated by Pascal's triangle, which is essentially the NCK, the combination formula. A, the value is going to be raised to a power, and it's going to decrease over time as B is raised to a power that will be increasing by 1 each time. Let's return to our problem in which our binomial of A plus B will all be raised to the 6th power. We'll write out the terms of row 6 from Pascal's triangle. We figure those out by going 6C0, 6C1, 6C2, all the way up to 6C6, which then produces the numbers 1, 6, 15, 20, 15, 6, and 1. Remember, there is symmetry involved with Pascal's triangle. I would then take your quantities of A and work those out into the various terms. So A to the 6th would go into the first term, A to the 5th would be put into the second term, A to the 4th would then be put in the third, and work it down until you get to A to the 1st and A to the 0. I don't need to show the 1 for A to the 1st, and I don't even have to show the A to the 0 because A to the 0 will be 1. Then you'll want to do the B terms, and B to the 0 will lead off the first term, but again, B to the 0 was 1, so we don't really need to write that. B to the 1st, we don't really need to write the 1 down, but we can if we want. Then comes B squared, B cubed until we get to B to the 6th. At that point, if you do need to do any more simplifying, go ahead and do so. And so what I did is remove all the coefficients of 1, and we can say that the quantity of A plus B, all raised to the 6th power, is A to the 6th plus 6A to the 5th B plus 15A to the 4th B squared plus 20A cubed B cubed plus 15A squared B to the 4th plus 6AB to the 5th plus B to the 6th. Let's demonstrate how the binomial theorem can expand the following expression, the quantity x minus y, all raised to the 8th. Now this example was chosen because it involves subtraction within the binomial. What you need to do is figure out what row 8 of Pascal's triangle is, and that would be 8C0, 8C1, 8C2, all the way up to 8C8. You can actually find those numbers, 1, 8, 28, 56. Remember, this is a sum, this is a series, so you will want to add up the individual terms, so don't forget to put your pluses there. Now that we've gotten the necessary values from Pascal's triangle, let's move on to the A plus B, or specifically the A part of the binomial. We need to take A, in this case specifically x, and we have to raise it to the largest degree, which in this case is determined by what our binomial is raised to, 8. So we will go x raised to the 8th. That will get multiplied to the 1, again from Pascal's triangle. Then we go ahead and we add 8 times x raised to 1 degree less than before. That's why it goes x raised to the 8 minus 1. Well, that works out to be x to the 7th. Then we move on to the third term, and we'll have to write again 1 degree less for x. So we'll now write 28 times x raised to the 8 minus 2, which actually is just 28 times x to the 6th. And we'll continue this process until you get down to x to the 0. You'll do the same thing with the negative y's. Notice I said negative y. You have to think of this as an addition problem. So over to the left, I wrote x plus negative y all raised to the 8th power. So you need to think of negative y being all raised to the 0 power, and then negative y all being raised to the 1st power for that next term, and negative y all being raised to the 2nd power for the term after that. And you're going to want to do that all the way up to degree 8. Now I recommend separating the negative from the y and put the coefficient of negative 1 to the 0 with the other coefficient of 1 where you got from Pascal's triangle. So in the second term, I'm going to have negative 1 raised to the 1st being multiplied by 8. In the next term, I'm going to take negative 1 and raise that to the 2nd power and multiply that by 28. And I'm just going to have y to the 0, y to the 1, y to the 2, all the way to y to the 8th. Remember that any negative value that's raised to an even degree, in this case negative 1 raised to 0 or 2 or 4 or 6, is going to produce a positive result, or in our case specifically a positive 1. While any negative 1 being raised to the 1st, 3rd, 5th, or 7th is going to still produce a negative 1, which then multiplied to our coefficients initially will produce our final answer of x to the 8th minus 8x to the 7th y plus 28x to the 6th y squared minus 56x to the 5th y cubed plus 70x to the 4th y to the 4th minus 56x cubed y to the 5th plus 28x squared y to the 6th minus 8x y to the 7th plus y to the 8th. Note that the terms were alternating between positive or negative. Our next example does not have multiple variables within the binomial. There's only a g in essentially the first spot. So when we're trying to expand the quantity 3g plus 4 all raised to the fifth power, remember, the steps for the binomial theorem do not change. You'll still want to work out row 5 of Pascal's triangle. And this part, I'm not going to tell you to do 5c0, 5c1. You'll just do it, okay? Now, as we apply our quote a to the fifth, a to the fourth, you have to understand that what's actually in the a spot is 3g. So you need to take the whole quantity of 3g and raise that all to the fifth power. And then you'll need to raise the quantity of 3g and raise all that to the fourth power, and then all of that to the third power and second power, first power, down, until you get down to the 0th power. Just as the quantity of 4 will be raised to 0, then the quantity of 4 will be raised to the first, and then quantity of 4 will be raised to the second, and so on. Now what you want to do is combine all the numerical values together so that you can produce one coefficient for each term. So take the 1, multiply it by the 3 raised to the fifth, and multiply that by 4 raised to the 0. When you're done with that, then you'll just multiply that result by g to the fifth. For the second term, you'll take the 5 from Pascal's triangle, multiply it by 3 to the fourth, multiply that by 4 to the first, figure out that result, and then multiply that by g to the fourth. And you're going to continue the process until you get to the last term. And if you do so, you will come up with 243g to the fifth, plus 1620g to the fourth, plus 4320g to the third, plus 5760g to the second, plus 3840g, plus 1024. Our last example is going to give us a good challenge because we have subtraction, we have multiple values, we have multiple variables, and those variables are raised to powers themselves. So, what are we going to do to expand the quantity of 9m squared minus 8n cubed and raise that all to the 7th power? We're just going to do binomial theorem. We'll start by using row 7 of Pascal's triangle. We'll take each quantity of 9m squared and raise it to the 7th, then the 6th, and the 5th until we get down to the 0. We're not going to think of our expression as being a subtraction problem, but adding a negative value. In this case, negative 8n raised to the 3rd power. And that whole quantity will be raised to 0. Negative 8n cubed, all of it will be raised to the 1st power. And we'll keep doing that until we get to the 7th power. It's important to bring those numerical values together to produce individual coefficients for each term. Take the 1, multiply it by 9 to the 7th, and multiply that by negative 8 raised to 0. Make sure your parentheses are around the negative 8. Otherwise, you're going to get a negative coefficient when you should be getting a positive coefficient. 7 times 9 to the 6 times negative 8 raised to the 1st. You're going to get a negative coefficient here, with or without parentheses. But again, when you go to the 3rd term and you go 21 times 9 to the 5th, if you forget the parentheses around the negative 8, it's going to produce a negative number on the calculator. But you need it to be positive because a negative times a negative is positive. Another thing you need to know is you got to remember how to do powers to powers. M squared is going to be raised to the 7th. You multiply the powers together, that will become m to the 14th. N cubed will be raised to 0. That's going to be n to the 0. It's going to drop out. If I look at the third term, m squared will be raised to the 5th. That will be m to the 10th. If you have n cubed raised to the 2nd, that will be n to the 6th. And what you may come up with for your expanded binomial is some very large coefficients, but in this case, some very large alternating coefficients, positive, negative. Your variables may not be m to the 7th, m to the 6th, but there's still a pattern to them, m to the 14th, m to the 12th, m to the 10th, as n is going n to the 0, n cubed, n to the 6th. So you may have a challenging problem. It may produce some very interesting terms, but if you follow the steps of the binomial theorem, it's not that big of a deal.